So this is my talk. It's about rectangle inequalities for data structure lower bounds. And by rectangle inequalities, I mean the richness lemma, not just the classic one. I also will prove a new richness lemma in this talk. And by data structure lower bounds, I mean lower bound for a particular one data structure problem, the nearest neighbor search. So there's an online note for the talk. It's very new. It's I just finished and uploaded it last week. You may check it out if you're interested. So, okay, for the nearest neighbor search, fixed metric space, and a database of n points from that metric space is given to pre-process into a static data structure. And at the query time, a query point x is given, which is also a point from the same metric space. And we want to find the data point which is the closest to this query point. Okay, this is a very important problem in computer science. And for lower bound, we study the decision problem, the lambda near neighbor. So here, fix our threshold for the radius lambda, and we only need to determine whether there is a data point which is lambda close to the query point. Okay, and we can also consider the approximate version. Here, another parameter gamma is given. Gamma is greater than 1, and gamma is for the approximation ratio. So this is the problem. The gamma lambda approximate near neighbor, gamma lambda ANN. So for this problem, we are actually querying with two balls in the metric space around the query point x. So we want to distinguish the case where there is a data point lying within this smaller ball of radius lambda from the case where all data points lying outside the bigger ball of radius gamma lambda. Okay, any cases between them, the answer can be arbitrary. So a particular interesting case to consider is when the metric space is the Hamming space with Hamming distance. In particular, d-dimensional Hamming space, where d is a sufficiently large constant times log n. Here n is the size of the database. Okay, so this is a high-dimensional setting. So the conjecture is the problem suffers from the curse of dimensionality. And for this high-dimensional setting, it is intractable to solve. So any data structure solve this problem must have very poor time-space trade-off. So this intractability is formally measured in this cell probe model. So this model we have learned several times, so I won't repeat. Just recall that S stands for the number of cells in a table, and W, the number of bits in a cell. And every query is answered by T cell probes. Okay, so together it's called a cell probing scheme with these three parameters. And okay, so for nearest neighbor search problem in d-dimensional Hamming space, depending on whether randomization or approximation is involved, we have two coordinates. Here is whether the near neighbor is exact or approximate. And here is whether the cell probing algorithm is deterministic or randomized. And by randomized, I mean Monte Carlo randomized. So a bounded error is tolerated. Okay. So the conjecture is the problem remains hard to solve if randomization or approximation is allowed individually. But when they are allowed simultaneously with both randomization and approximation, certain techniques like locality-sensitive hashing or dimension reduction can be applied. Okay. So we expect similar lower bound for these three quadrants, but different for this one. So these are the first generation data structure lower bounds for this problem. Okay. So there are several others I didn't mention. Here I just list the last step of the first generation data structure lower bounds. And they are all proved by the richness lemma, the classic richness lemma for asymmetric communication complexity. And for randomized approximate nearest neighbor search on polynomial space, there is a tight bound. So you can already tell the difference. And this D over log S bound for cell probe complexity is the highest lower bound we can prove with communication complexity. Right? So because within this many rounds, Alice can tell the entire query to Bob, and Bob can solve the problem locally. This is something we can do in the communication model, but not in the cell probe model. And this fundamental barrier was overcome by Patrascu-Thorup, their self-reduction technique. And with the cell sampling technique, the randomized approximate near neighbor has this kind of has this lower bound, so it's quite similar. But the numerator cannot be D because of this upper bound. And by applying the self-reduction technique to the non-deterministic data structure, in a previous work, we prove lower bound with this form. This last lower bound matches the highest known lower bound for any static data structure problem. So Casper's polynomial evaluation lower bound. And it behaves differently for polynomial space and near linear space and also linear space. And for all these lower bounds, this one is proved by the round elimination. And all others, other lower bounds are more or less related to rectangle-based techniques. And I'm not going to talk too much about this last lower bound of us. I'm going to talk about something new. I'm going to talk about the average case lower bound with a similar spirit like the last talk. So the input instance is random. So I remember I heard this kind of a complaint from some of my colleagues who work in practical fields, that our lower bounds, because our lower bounds are worst case lower bound, and their data are some real data generated from some real world distribution. So probably it's still possible that probably the problem is easy to solve on average on the real data, right? So, but I'm not so convinced that the curse of dimensionality breaks for average case. I believe the problem is still hard to solve on average. not just that, I think the problem is hard to solve because it is hard to solve on average. Because there is a very recent upper bound, a recent work on the data-dependent locality-sensitive hashing. It discovers that a key step to solve the nearest neighbor search is to solve the problem on a random input, where every data point is sampled uniformly and independently from the metric space. But the complaints of my colleagues, they raise some valuable points that the dimensionality as well as the complexity of the nearest neighbor search problem should be studied with respect to input distribution. And for data structure problem, this input distribution is a distribution over pairs of queries and databases. And for deterministic algorithms and for multicolor randomized algorithms, the average complexity can be defined in a standard way. Okay, and now let's review the state of arts for the average case complexity. Among all these lower bounds, this lower bound is made explicit for the average case. And retrospectively, the classic richness lemma actually also hold for average case implicitly. But the round elimination lemma does not. Because a key, I think, a crucial step in the round elimination lemma is to apply Yau's min-max principle to every possible input distribution. And the self-reduction technique does not directly apply to average case, at least not this natural distribution where every data point is sampled uniformly and independently from the hypercube. Where these average case lower bound are all for this natural distribution. And for the deterministic setting, almost all lower bounds, especially the new ones, does not hold for do not hold for average case. So that's what I'm going to deal with. So we can prove this kind of lower bound for the gamma lambda approximate near neighbor in d-dimensional Hamming space on this this input distribution, where every database point, every data point as well as the query is sampled uniformly and independently from the Hamming cube. We proved this lower bound for the average case cell probe complexity, T. So, yeah. But still, this is just an idealized distribution, right? So, could be not like the real world distribution. So it's worthwhile to establish this lower bounds with respect to certain dimensionality property defined for the metric space with respect to particular distribution over the metric space. And this is done by the notion of metric expansion of this paper. So let n sub lambda of x denote the lambda neighborhood of point x, which is just the lambda ball centered at x. And the lambda neighborhood of point set A is just the set of points reachable from A, from set A within distance lambda. Okay? and consider a probability measure mu over the metric space. We say the lambda neighborhoods are weakly independent in this metric space. The lambda neighborhoods are weakly independent under this distribution if all lambda balls are this small. The measure of all lambda balls are this small. So the union of n lambda balls together still leave a constant fraction of the space uncovered. Okay? This 0.99 is just an arbitrary constant less than 1. And next is a key concept. We say the lambda neighborhoods are expanding. This expanding, phi per c expanding. If we have this, so this is our metric space. If for any set A of volume bigger than 1 over phi, for any such set, within distance lambda, it grows into entire space, except for a volume of 1 over c. Okay, so this is basically just the vertex expansion of the metric. It gives isoperimetric inequality for the metric space. So it says this sufficient large set must grow into very large, almost entire space except this remaining small region. And with this concept, with these two concepts of metric expansion, we can prove a lower bound for the gamma lambda approximate near neighbor in any general metric space with input distribution where every data point and also the query is sampled IID from this general measure distribution over the metric space. Assume that, making these two assumptions, the gamma lambda neighborhoods are weakly independent. So the bigger balls are small. So the bigger balls are this small. And the lambda neighborhoods, the smaller balls, are expanding. So these two seems like two contradicting properties. And with these assumptions, we have a lower bound of this form. For the average case, deterministic approximate near neighbor in general metric space. Okay? And this second lower bound is not too useful because it's always much higher than the first one. That's for the reticular setting of S and W. So only the first one does matters. And our lower bound for the Hamming space, near neighbor, is a consequence of this because in the Hamming space, in the Hamming cube, we can have such expansion where from any under uniform measure from any set of 2 to the minus of C1 D measure within some distance C0 D, it can grow into almost the entire space except for also an exponential small region, right? So for any C0, we can find such C1 and C2 constant. So this gives us phi and C as 2 to the D level. So the log of them is the D and the D, right? So D over the log of SW over ND. So this theorem connected the average case self-probe complexity to the expansion property of the metric space. And it is proved by the richness lemma, but a stronger version of the richness lemma. So remember that, in Casper's talk and last week's talk, the classic richness lemma is proved for asymmetric communication complexity. So it basically says if your problem, your decision problem, as a Boolean matrix is dense enough of ones, dense enough in ones, and it also has an easy communication protocol, then it has large enough monochromatic rectangles consisting of only one entries. Okay. Here, the density as well as the size of the rectangle is measured by this general product distribution. So if for your problem you can show your problem is dense and also has no large one rectangle, then you have the lower bound. Okay, and this is for communication protocol, and translate back to the CellPro model, it gives you lower bound of gives you rectangles of this size. Okay, with S, W, and T, these parameters. So we prove a stronger version of the richness lemma, this new richness lemma. Okay, the spirit is the same. It says if your dense problem has easy solution, then it has large rectangle. But now we have two improvements. The first one is it now made explicitly for the average case complexity. But it's not a crucial improvement because, as I mentioned, the classic one also holds for the average case implicitly with some modification. The real improvement is this part. It now gives an entire family of monochromatic rectangles instead of just the one. So to prove a data structure lower bound, we only need to pick any one rectangle from the family to refute. So you can just pick any convenient one, or the one which gives you a highest lower bound, to refute that such large rectangle exists. And this family of rectangle has a smooth trade-off between the columns and rows, scaled by this parameter delta. Okay, and that's a real advantage. And also, it makes this richness lemma separate the CellPro model from the communication model. So now let's prove this. Okay. It is proved by the cell sampling. The idea is quite simple. A key step is to prove this the following claim, that there's a large amount of good databases. So actually, in fact, a constant fraction of databases are good in the following sense. For any good database, when it is stored in a table, we can always, for any parameter delta within this range, we can always find a subset of delta cells. So the amount of positive queries resolved by revealing the contents of only these cells is as large as this. Okay. So every good database. By positive query, I mean the query X, where fxy equals 1 for this database Y. Okay, so for every good database, it always has a subset of very useful cells that can resolve many positive cells. Okay? So we can imagine that we have this deterministic procedure that for every good database, it always find the most useful subset of delta many cells that can resolve the maximum amount of positive queries for you. And let's denote by omega the positions and contents of these most useful delta cells. Okay? And in this way, every good database is assigned deterministically with an omega. And there are at most these many possibilities for omega. Because an omega is just a tuple of positions and also contents of delta cells. So it's just the positions and contents of delta cells. So at least a fraction of this good databases are mapped to the same omega. So in our matrix, at least a fraction of good databases all have the same map to the same omega. And so this means these databases all have the same contents at these positions. So in the cell probe model, by the determinism of the cell probing algorithms, it means it must resolve the same set of positive queries. And by this claim, this set of positive queries is pretty large, right? It's pretty large. So now it gives us the large monochromatic rectangle. It gives the columns and the rows of the rectangle. And it must be the one rectangle, monochromatic one rectangle, because all queries are positive. Okay. Okay, so that's all for the proof for this richness lemma. It only remains to show this claim, this very first claim. And so we can do this by easy argument, by an easy probabilistic method. So fix any database. Let's consider the fix any column in this matrix. In this matrix, fix any column. We consider the set of rows with ones in this column, right? The set of positive queries, and also the conditional measure induced by the over these ones, over these rows induced by the measure over all rows. Okay, and remember that we assume that our problem is overall is dense enough, and also the overall average cell probe complexity is bounded. So by averaging principle, it's easy to see that we have a constant fraction of columns which are good. In the following sense, that every good column itself is dense enough. So this column is good. It has a constant fraction of ones. And also, the average cell probe complexity over these ones is bounded. So that's just a straightforward averaging principle. It's nothing fancy. But from here, we have the good databases. We only need to find the useful cells for these good databases. So for any good database, when it is stored in a table, we know that this table, this entire table, can resolve a large amount of positive query with a bounded average cell probe complexity. Okay? And here, these are the positive queries, and these are the cell probes to resolve them. And it is It gives us a hypergraph with cells as vertices and hyperedges, a hypergraph with cells as vertices and positive queries as hyperedges. Right? This bipartite structure is just the incidence graph for that hypergraph. And what we know about this hypergraph, we know that it has many edges, hyperedges. And also the average size of the hyperedges is bounded. Okay, because that's just the average case complexity. Then by the probabilistic method, we can show that for any delta, there always exists a subset of delta vertices that induce the subhypergraph with many hyperedges. Okay, it's just a easy probabilistic method proof. We can imagine that we sample the vertex with this rate, and since the average number of vertices involved in the hyperedge is bounded by this, it's natural to expect we have these many hyperedges sampled in expectation. Okay, so this pretty much proves our claim that we have a constant fraction of good databases, where every good database exists a subset of very useful cells that can resolve many queries. So the rest of the proof just follows as I mentioned. Okay. So that gives us the richness lemma of this form. But to use it, we need to carefully choose our parameter, right? That's kind of tricky. So to make it more convenient, let's consider a natural family of data structure with a conjunction form. I call it a conjunction problem. So for conjunction problem, every database is always a tuple of endpoints from some domain. And the database, okay, so the conjunction data structure problem F is defined as a conjunction of binary relation between the query and each of the n data points. Okay, and this binary relation is defined as point-wise Boolean function G. So it's like a constraint satisfaction problem where the query enforces a constraint for every individual data point, and all of them must be satisfied to pass this query. It includes a large family, a broad family of natural data structure problems. For example, the near neighbor, the gamma lambda approximate near neighbor can be described in this way as a conjunction problem, where this binary relation, the point-wise function G, is the gap distance. If it's a Hamming space, it's a gap Hamming distance. So it takes 2 points, x and yi as input. X is the query and yi is the one data point. It returns 1 if they are far apart, 0 if they are close. Otherwise, it's arbitrary. Okay. So notice that we use 1 to indicate a far apart non-near neighbor case. So the conjunction of them means if none of the data points is close enough to your query, it's a non-near neighbor case. It's a 1. If any of them is a near neighbor, it's a 0, right? So many other natural data structure problems can be defined in a similar way. And for conjunction problem, we consider a natural input distribution, which is a product distribution over all data points. And we can have this very convenient lower bounds for conjunction problem, Remember that for richness lemma, to prove a lower bound, we need to show a data structure problem. A big data structure problem is dense and also has no monochromatic rectangle. But here, consider this natural family of conjunction data structure problem, where F is the big data structure problem, and G is the smaller one, pairwise function. We only need to say that G is dense enough, and the G has no rectangle of this size. Then we automatically get this lower bound for the big data structure problem. And here G is very dense, actually. The density of 0 in G is 0.99 over n. And G has no rectangle of this size under this measure, product measure. And this is actually just a consequence of our new richness lemma. First of all, with this density of G, so the sparsity of zeros in G, by the union bound, F is dense enough with ones. And also, if G has no one rectangle A times B of this size, then F has no rectangle A times B prime of this size. Mu to n A prime greater than this. So it's a product distribution. Also, there's a product here. That's because of the conjunction. Okay. So now apply the richness lemma, and this new richness lemma. We choose this parameter within this range. We can always choose a parameter out of this range to satisfy this inequality. Okay, to make this true. And first case, if this parameter is already outside this range, it immediately gives us this useless lower bound. Otherwise, we can apply the richness lemma. So F has a rectangle of this size. Okay, but we know that we know this thing is greater than this. Okay, and we know that F has no rectangle like this. So it must be true that mu A is less than 1 over phi. So this gives us the useful lower bound, because this and this choice of delta. Sorry?
You prove that one of the lower bounds on D is true?
Yeah, either this or that. Because this one is too high, always too high then, for practical choice of S and W.
So it could just be that the T is the first one that over time.
It's either this or that. Right? Logically, we can only take the minimum one to. Yeah. So if this one does not, no. It can be true. So, so either this or that, right?
Are you telling me that both are true at the same time?
No. So this is the case, right? Either this or that. If this is not true, then we have this. So either this or that. It's quite typical for asymmetric communication lower bounds. With this, either Alice sent this or Bob sent that, but one of them is kind of too high.
But is there no hope of proving the second one unconditionally?
No,
Because you're basically telling me either something that is not so strong or something.
No, I think no. I mean, if you choose your S and W within some suitable range, like this is S is a polynomial of n, W is log n. Then this one is always higher than this one, right? So altogether, so either this or that means you just have this.
Oh, so the first one is high. So that's
Right. That's what I'm saying, yeah. Yeah. So just ignore this, okay, just ignore this. Only this is a lower bound applied. So yeah, so this proved the lower bound for conjunction problem, okay? This is quite convenient because conjunction problem is represent a natural family of, large family of natural data structure problems. And this lower bound just reduce the data structure lower bound, average case data structure lower bound to the rectangle property of this pairwise binary relation. It's very easy to analyze. For example, for back to the ANN, the approximate near neighbor.
So you have different G's for each I?
You can have, yes, you can have a different G for each I. Sure you can. So actually this is the lazy notation because this arbitrary may have different way to be arbitrary for a different I. So yeah, but doesn't matter. It doesn't change anything. So recall that this G for the AN is the gap distance function. So when this G is the gap distance function, with 1 indicate the non-near neighbor, the far apart case, then the weak independence of the metric space implies the density of G. And also the expanding property of the metric space implies refute the existence of large rectangle in this pointwise function. So let's verify this. The first one is pretty easy because as I said, if the gamma lambda balls are small, in this small function G, every row X has a very small number of zeros, okay, small fraction. So overall, the fraction of zeros is small. And second, if the metric space is expanding like this, then for any monochromatic one rectangle in this G, in this gap distance function G, because it's one rectangle, it has no zero. It means none of the point in B can be lambda close to any point in A. So B is a subset must be a subset of a complement of the lambda neighborhood of A. Okay? For measures, it means mu B is less than 1 minus mu lambda neighborhood of A. Okay? And assuming that mu A is greater than 1 over phi. And by the expansion property, we have this greater than 1 minus psi. So this is smaller than 1 over psi. Okay? So we cannot have rectangle like this by this rectangle, by this expanding property. Yeah? Okay, enough. So we proved this main theorem. Okay? From expanding property imply from the metric expansion, which implied the rectangle property of gap distance function. And back into the, for the Hamming space, we can choose this gamma lambda radius as this bigger ball, this radius of bigger ball as this Chernoff bound threshold. So by the Chernoff bound, the bigger balls are small, this small, so it's weak independent. And by Harper's isoperimetric theorem, in Hamming cube, the Hamming balls always have the smallest vertex expansion. So we can have, we can just safely assume this A without the loss of generality, assume it to be a Hamming cube. So we can have this kind of expansion. And which gives us this lower bound of this form for the approximate near neighbor, the average case complexity for approximate near neighbor. Okay, the last note is all of the proofs work for the non-deterministic data structure. So I really like this example that Casper mentioned in his talk. So for one-dimensional nearest neighbor, assume the data structure is sorted. So I review this two cards for you. It proves for you that if you query is 8, it proves the nearest neighbor for you. This is the non-deterministic cell probe in a data structure. And I really think non-deterministic data structure is the real thing because in a network, imagine in a network, your data structure is a network. A packet relayed is relayed in a network. And we don't care too much about the times the packet relayed, but we fix the size of the packet. And when it terminates, it must be sure about the answer, right? So that packet, along with the local information at the last stop, is the certificate. So it's a real thing, I think. So wrap up. This is what we just proved for Hamming nearest neighbor, average case. And here, for randomized approximate near neighbor on polynomial space, I think for average case, we may have a constant upper bound. So the complexity becomes different. So the lesson here is that the rectangle-based techniques, such as richness lemma, is really robust. It works for average case, and maybe also even for the non-deterministic case. But round elimination techniques such as round elimination is really only for the adaptive, to deal with the adaptivity, worst case adaptivity. The last thing I want to talk about is a question, that natural question, whether we can make this technique, this framework, use this framework to prove the same lower bound for the randomized exact near neighbor. The answer is probably no, because because we do not have a suitable expanding property in the Hamming cube for that case. Because in that case, we can still manage to prove the similar thing for the conjunction problem, where the conjunction problem, the pairwise problem is just the lambda distant, lambda near neighbor, or lambda non-near neighbor. But now we want to refute the existence of a large size dense rectangle, not one rectangle. So every column is almost all one except for a epsilon fraction. So translate to the metric expansion. To refute the existence of dense rectangle, it's almost like to prove something like this. So for any A and B in the Hamming cube, subset of point in the Hamming cube, arbitrary And we know that the pair of near neighbor, lambda near neighbor, between them is really sparse. Okay, is epsilon. It has an epsilon distortion times the average case. Then we want to get something this strong, too strong. Mu A times mu B. Remember, these are all for the uniform measure. So, sorry, smaller than this. Okay, has this exponential small. The product of these two volumes is exponential small. When epsilon is 0, this is just this is just the Harper's inequality. But for non-zero epsilon, it has a counterexample. The best that we can get is the reverse hypercontractivity inequality, but that thing is that can only give very weak bound. And also that thing is tight. Okay, that's the last thing I want to say, and thank you.